So let's take a look at what we can do with the results after we get the adjusted values and we calculate the residuals. And the residuals are the Jacobian times the x adjusted minus the y vector. The y is the vector of the knowns. And what are these residuals good for? Well, with the residuals, we can calculate the standard deviation. And that's the little sigma. And it's found in the FS handbook. And this is the handbook that's allowed by NCSS to be used during the Fundamentals of Surveying exam. This is the 2020 version. Version. And it's somewhere there we go. So there's not much on adjustments in the licensing exam book or the cheat sheet. Standard deviation is basically the sums of the squares of the residuals divided by n minus 1, where n is the number of observations. So it's the square root of the sums of the squares of the residuals divided by n minus 1, or it can be divided by n. This is for a sample if n is less than or equal to 30, and this is for a population if n is greater than 30. And this is basically the square root of v transpose v divided by n, or n minus 1. And this is called the standard deviation. Standard deviation. And the square of this, sigma squared, is called the variance. The standard deviation tells us how close the measurements are to each other. The smaller the standard deviation, the closer the measurements are to each other. And conversely, the bigger the standard deviation, the farther away the individual measurements are from each other. So in surveying, in surveying, let's stick to surveying. The user always wants a low standard deviation. Well, usually always wants a low standard deviation. A low standard deviation means high precision. And conversely, a high standard deviation is a low precision. And precision has nothing to do with accuracy. Accuracy is related to error. accuracy is how close to the errorless value the measurement is. And the distribution of the measurements usually takes on a Gaussian distribution. This is a Gaussian distribution, and there are all these little metal balls or pellets falling into this container. Each container has these little bars, and this is the theoretical value that it should have. This is the theoretical Gaussian distribution, and you can see that it actually follows it. The example, the real life example, kind of follows it pretty accurately. That is the measurements. Well, let's take a look at this Gaussian distribution. So if a distribution is Gaussian, it looks like this. It looks like a bell curve distribution. So this is the Gaussian. Or bell curve, or normal distribution. These are all synonymous with each other. The x-axis is, so the x-axis contains the measured value, and the y-axis is the number of measurements. And this is called a histogram, and it tells us how the measurements are distributed. For a bell curve or a Gaussian distribution, the number of measurements mostly cluster around the average, and the farther away we get from the average, the less and less measurements there are. It's a symmetric distribution, that is, both sides cover the same area. And for a Gaussian distribution, the 1 sigma range, the standard deviation. So this is the average minus 1 sigma, average plus sigma. This area covers 67% of the area of the distribution. The 2 sigma range this is minus. So the 2 sigma range covers about 95% of the data. And the 3 sigma range 3 sigma range covers 99% of the data. And these values are going to be further discussed later on, but these are 3 values that should be remembered. 1 sigma range is 67%, 2 sigma range is 95%, and the 3 sigma range is the 99%. So let's take a look at a presentation on histograms. There are 3 types of errors that we can distinguish. Random errors. These cannot be eliminated. They come from user error, instrument error, pointing an instrument in not exactly the right direction. Systematic error, these can be corrected if they're known. Systematic error is using the wrong unit of measurement. And a blunder, say writing down 19 instead of 91. Once again, this can be corrected if the error can be found. Random errors cannot be corrected. That's why they need to be adjusted for the most likely or the adjusted value. And let's say we have 5 measurements. We can calculate the average of these. We can calculate the standard deviation. Since this is less than 30, we use n-1 to the square root of the sum of each measurement minus the average divided by n-1. The median value is the value that's right in the middle. 45 and 46, these are 2 measurements that are smaller than 47. 48 and 49 are 2 measurements then higher than 47, so 47 is the one that's right in the middle. The mode is the most frequently occurring measurement. And it's not unique here since each of these occur with the same frequency. That is, they occur once. So basically, histograms are bar graphs. They're frequency representation charts. So let's take a look at how much time does the 1161 mile Iditarod take. And these are the contestant times in hours. The minimum is 236. And the maximum is 360. And let's divide this into 5 classes. So basically create 5 bars and aggregate the data into 5 classes. And this just sorts the data from the lowest to the highest. So how to compute the class width? Take the difference of the lowest and the highest divided by 5. which would be 24.8, so we can round that up to 25. So each class gets as a 25-hour width. From 36 to 260, there are 4, or 26, from 236 to 260, 261 to 285. So 25 hours is the width of each class, 1, 2, 3, 4, 5, and we have 5 bars. And there's the distribution of the 5 classes of the Iditarod race. The x-axis is the measured value, the y-axis is the number of measurements. And there's another type of histogram. This is the frequency histogram. It contains the actual data, and there's another one called the relative frequency. It has the same shape, exactly the same shape as the frequency. The x is once again the measured value. However, the y-axis, instead of actually containing the number of measurements, it's the percentage of occurrences. So this contains the actual number of occurrences, and this is the percentage of the occurrences. And why would the relative frequency histogram be useful? Because it can compare data that have widely different number of occurrences or widely different number of measurements. One data set contains 1,000 measurements, the other contains 20. The number of measurements in both data sets is quite different, and so instead of comparing the actual number of measurements, we can compare the relative frequency or the percentage of occurrences. Over here, if we add up the number of measurements for each class, we get the actual number of measurements. That is, the area under this contains the actual number of measurements. The area under this, since it's a relative frequency, is 1. Or 100%. So if we add up the individual numbers over here, we're going to get the actual number of occurrences. And in this example, we are asked to create a histogram, height in centimeter of 50 horses, and make a histogram with 8 classes. Since we know that there are 50 horses, if we add up the number of occurrences in each class, we're going to get 50. And the relative frequency, so this is the frequency, this is the relative frequency. 10 out of 50 is 0.2 or 20%. 12 out of 50 is 0.24 or 24%, and so on. If we add these up, we're going to get 50. This C frequency represents the cumulative frequency. So the first class represents 10. The first and the second class represent 22 horses. 10 plus 12 is 22. 22 plus 17 is 39, and so on, all the way to 50. So this is the frequency histogram. And the relative frequency histogram has exactly the same shape, but instead of the number of occurrences, we get the percentage of occurrences. So this would be 10, 12, and 20, 24, and 34%. So this is 20, 24, and 34%. And there it is for the same data set. And we can also represent this data, instead of a bar graph, we can represent it with a polygon graph. And this is the cumulative frequency histogram from the lowest to the highest, and it ends with 50 horses. And these are some other shapes besides the Gaussian distribution. The uniform distribution. It has the same number of occurrences everywhere. And what would an example of this be? This is like the dice rolling game. Theoretically, there's an equal chance for somebody to throw 1, 2, 3, 4, 5, or 6. So that's why it's called a uniform distribution, because there's an equal chance for each result. And if we take a look at the relative frequency distribution of this, there's a 1/6 chance that somebody can throw a 1, a 2, a 3, a 4, 5, or a 6. Add them up, we get 1, or 100%. Now, since nothing is perfect, some distributions are not going to be perfect Gaussian distributions. They're going to be skewed a little bit to the left or the right. So it's going to look like this, or it's going to be something like this. And in the worst case, this is a bimodal distribution. It has 2 peaks. And it's minimum right near the average of the measurements. So these are the skewed, uniform, and bimodal. And in surveying, we always want our distribution to be very narrow. That is, it should look more like this, well, than with a wide distribution, something like this. Because a narrow distribution means that it has a small standard deviation. And a wide distribution means it has a high standard deviation.